Someone answer me. What is your understanding of a data structure?
So,
A data structure.
Go ahead, Jack.
A data structure is a way of holding and sorting individual pieces of data in a variety of ways. It could be stuff like lists or arrays. It could be databases. It could be strings.
Okay. What pieces of information? How do you hold it all together?
The way I think about this is like via keys and values. You know, you either have like an index or some sort of like pointer that then has an associated value, and then you manipulate those two things to do whatever you need to do.
Okay, you said a magic word there, which is pointer. How many people know what a pointer is? We're going to go all the way down to the hardware and we're going to come all the way back up. So we're going to start from like the very basic thing. How many people know what a pointer is? And it can't be Jack this time.
We've talked about pointers looking at classes in memory.
Mm-hmm. Yeah, but what is a pointer exactly?
It's a reference to a memory location where a piece of information is stored.
Exactly. So every data structure that you have is by definition a pointer. It is a point at the very core of it. It is a pointer to a location in memory. That location in memory has a size. It has kind of a set of variables. It has, and each of these is kind of like organized in a specific way. And all of that memory for that object is co-located. So it is a space of memory. It is a physical space of memory that defines your data structure. It's called an object. It's literally like a block of memory. So I wanted to kind of start there as an understanding of, you know, the core of what an object is, because all data structures come like at their core, they all are an object. They're all a self-contained object. They can have pointers to other objects and other variables and other definitions, but they are in essence a single object. As you come back up, you kind of get more of that abstraction built in. So, you know, coming back up, we have an abstraction of, we can have labels, we can have not necessarily unique, yes, but memory addresses are unique. So you can have two objects on the abstraction level that point to the same address, but they are physically the same object. If you have two objects that are equal, they may not be physically located in the same place. They may be physically located in the same place. That gets into kind of like different types of passing by reference, passing by copy, but we're not going to go into that. You can understand it as a block of memory. So bringing it back up, you have a name. How many people know what an equals is? When you say in Python, name equals Sophie. How many people know what that actually does?
Assignment statement.
What?
An assignment statement.
It's an assignment statement. That Sophie is a memory, is a object, is stored in memory. And what you're saying is this variable name is assigned to this place in memory. So now that we've kind of like covered, does anybody have questions? Who has questions is a more specific question to ask. Who has questions? Not does anybody have questions? Who has questions?
Would it be safe to assume that that's just called prototyping though? Like that variable you created is just a prototype of the object?
No. So it's complicated and I'm not going to go into it right now. It's not that like it is, but I don't want to like go into like random detail tangents because I'm very quickly I very quickly go on tangents into random directions. So we're just going to kind of like try and stay on track. In the physical sense, which is where I'm trying to start at, it is literally assigning a memory address, a memory location, a pointer, which is an actual value to that register, which is, there are a certain number of registers in the CPU and in the computer that, you know, you're working off of, and it's assigning that specific register. I'm not going to go into how like a program is written in the physical binary sense, but it is assigning a numerical value, which is a pointer to a location in memory, which is an offset. That was very complicated and I went on a tangent, but so now that we've kind of got that idea, how would you define a class? Like how would you define a code platoon class? If you were saying, I have this code platoon class, how would you define what the essential pieces of it are to identify each one? So you have the students, you have the teacher. What else do you have?
Class name.
Class name. What else? What else would be useful to know?
Curriculum.
What?
Curriculum.
Assignments.
Assignment.
Like the work to do, not like assignments.
So there's a difference between curriculum and assignments and the name. What's the difference?
So you're assigning attributes to
Attributes, exactly. So the way I like to think about, there are two pieces to a data structure. There's the template that we write, and there's the actual attributes that we assign. The template that we write is common to all of the instances that we create. And an instance is a unique instance of that data structure. It's a unique physical piece that you're creating. And that's why I was going into kind of the physical aspect of it versus the abstraction of it, because the template is the format that you are assigning to that instance. So it's the format that it follows. So if we take, it's kind of like the attributes that we need and the pieces that are common across all instances. So let me open PyCharm. We're gonna have fun. Apparently it's been a while since I opened PyCharm on this computer.
I've got a quick question. It's kind of off topic though. So since you're working at Apple, what kind of language do you use the most?
Oh, that's a complicated question.
Oh, never mind. I was looking for something simple.
No, it's not complicated. I use a lot of languages. I use everything from, you know, Bash code to all the way up to Python and Java and C++. So here's an interesting distinction. I see some discussion about memory and CPU and RAM. RAM is very quick cache lookup. I don't do app development. I do backend server development. So I work on this stuff. So when you do app development and you use CloudKit, I work on developing CloudKit. So I work on developing the databases and search indexing that functions for those databases. Weird thing. So the difference between RAM and like hard SEO, I don't know what SEO stands for. I'm seeing so many comments, so I'm responding to them, but so I am talking about memory as an abstraction. The difference between caching and the physical hard disk is that a caching is a quick lookup. It's a smaller location. So tangent time. When we first started building computers, we had physical disks, kind of like a CD, or it was a CD. And lookups on those disks were extremely complex because we actually had to go through and actually do an offset. Now that we have solid state drives and everything like that, the cache has actually become less useful. Because it used to be the kind of like the solid state. The reason that we had a cache was because it was a smaller version. And so it took less time to look up, and we were constantly overwriting so that we could hold pieces, objects in memory closer to where we could access them faster. And so, you know, when I do talk about memory, I kind of talk about memory as a solid state memory. Which is a fast lookup. It's kind of like a lookup between an array and a linked list. The disk is a linked list and the solid state is an array because you can just kind of like go straight to the offset. It's really interesting to get into the hardware. But okay, so we're looking at, give me 2 seconds. Okay, can I share? Any other questions? All Python takes forever.
So
My
it-
computer shuts down every evening, which is why it's just.
so is PyCharm a standard?
It depends. You can use pretty much anything. I like to use the JetBrains stuff just because, you know, once you get to a standard, it kind of becomes, you learn all the shortcuts and you learn everything. And so I've mapped all the Vim shortcuts into PyCharm and into, you know, IntelliJ, but you'll find your own, and you'll find your own kind of like standard that you want for, you know, for yourself. Jesus. I think it uninstalled it overnight.
I kind of have a quick question. When you were going back to the equals, when you gave the example of equals like Sophie, right? Like, so you would initially, you're assigning like a variable to initiate the object of Sophie. Does that sound right?
So I'm going to go down to what it's doing kind of like in the back end. So what you're doing, and this is really important, not just for kind of like back end engineers like me to know, but I find that it's also important for front end engineers and full stack engineers to know, because you need to know what your program is doing, because otherwise you can't optimize it. So if you're constantly assigning new variables, you need to know that you're constantly writing new information in memory. So those little tiny micro optimizations come into play of, you know, reassigning things, which reassigns a pointer rather than writing and then assigning a new one and taking up space, because memory is really finite. So to get back to your question, which is kind of like what's actually happening in that instance, like in that moment. So it's saying, okay, I have this name. I'm pointing it at a place in either the cache or the register, which usually it's a register when you're dealing with like like computational program. And I'm saying, and I'm taking I'm taking a slice of memory and writing this, and then I'm saying this register gets this memory address and off, which is technically an offset from 0. So it's placed in the memory array where that lives. So whenever you assign a variable, you have to understand. Sometimes when it's an integer, so when a small object, so objects have different sizes, obviously. So a string is rather large and can be kind of like exponentially big. An integer is a very set amount. There's a reason there's a max int. It's because it only takes up this number of bits. And so those can be assigned directly into registers if you don't need to keep them around. And the compiler does all sorts of optimizations to kind of like do dead code elimination and SSA optimizations to really streamline your project. So, your compiled code is different, but okay, so we're going to define a code platoon class. Throw stuff out.
Need a initializing method, a double under.
We're going to start with what needs to be there. And then we'll go into the map.
Staff, TAs.
Okay. We're going to type things because that's important, but yeah, we should do an init. Okay, so do self dot what? Someone said? TAs?
Yep.
Can you tell I've been coding in Java too much? Yeah, colon at the end of that. What else?
Instructors.
Okay, what else?
Class members or students.
Okay, what else?
Curriculum.
Do we want to put the curriculum here? Remember what we said about attributes versus template. If something doesn't change, it shouldn't be allowed to be set. It shouldn't be allowed to be, set. It should be, you should make it finalized. So this goes into more of that, but you should define it outside of the initialization because it should be what we call static. And static is a definition where it is something that is able to be accessed outside of an initialized object. Do people know what initialized means? I'm seeing a lot of nods.
It is set to when something is created.
Kind of, yes. It's initialized basically means created. A little bit.
So it's like you're bossing the computer around and telling it to initiate this class.
Oh yeah, no, we are definitely bossing the computer around. Yes. Yes, we are God when it comes to the computer, and it's a lot of fun. So there is a huge difference between, so what we're creating right now is a template for how this class should look. And we're going to get into more complex classes. I'm kind of rushing because I've not got a lot of time with you guys. So these are attributes, right? How do we usually define these? How do you guys think of how to set these?
Yeah, usually we do self dot whatever the name equals the name itself.
Okay, but how do you take in the information?
either as a parameter to the function or read in from a file in some way.
There's a third way.
We've
User.
recently been playing with CSV files.
That's kind of reading it in from a file. So you can take it in as a parameter, read it from a file. What's the third way?
User input.
Sort of. There's something called getters and setters. Have you guys heard that before?
Yeah, I've heard it.
Yeah, I've
I
definitely
have.
heard of it in C++.
You
Wait.
can do them anywhere. It's kind of a concept, not a actual language feature. So getters and setters are where you do a get def set instructors. That's a getter and a setter. That's a setter. Wait. You don't want to use that. So for example, if we wanted to create a class and then we wanted to go through and actually set, if we wanted to be able to change it, we want to be able to have, and this gets into designing objects. You want to think about your use case, right? So when you create the Platoon class, what are the things that aren't going to change? When you create it, there are pieces that aren't going to change, right? So what won't change? Usually the name won't change. So
Maybe
that
like class hours.
class hours, that's
Location of it.
would the location change?
Usually no. If it's like a brick and mortar, I think of it kind of staying in the same, at least city wise, it would stay.
Would it? What's these are things that you need to think about when you're creating these pieces. Murphy's Law. What's the worst case scenario?
Rona.
That it might move eventually.
Exactly. So what do you need to build in to to this template that you're creating? You're creating this and it's going to be standard for every single instance. So what are the pieces that you need to think about?
To make it flexible.
You need to make it flexible. You need to make it strict but flexible, which is such a weird concept. But in terms of the name, you know the name should never change. And you almost want to lock in the user. This is where you think about kind of like user experience, or I do. This is as close as I get to user experience. But you need to kind of say, how is the user going to shoot themselves in the foot? And how do I protect them from doing that? At the same time, making it possible for them to be able to use this in the way that they need to. So we're going to take it and we're going to say, okay, well, the name should never change, right? But maybe you should be able to edit the hours, but maybe you should have to know the hours to edit them. So what I would do is take a do that. And we're getting into a little bit of user experience here, but it's like so important to think about when you're creating it. Because you guys seem to already know kind of like be very quickly understanding the like core stuff. But before we go on, someone who hasn't spoken, and I am going to call you out. Let's see. Actually, I can't see names. So Someone who hasn't spoken, ask me a question. I know someone has a question.
I have a question. Why are we passing in old hours and new hours? Why can't we just set new hours?
I love that question. That is a great question. So what happens, Murphy's Law, right? What happens if the person who's changing the hours doesn't know what the current hours are? What if they get their times mixed up? We're working across time zones, right? What if they try to set the new hours in Pacific and the old hours are in Mountain Time?
It'll catch because they'll have to figure out why the old hours don't match up if they try to put it in their time.
Exactly.
So you're preventing the user from destroying everything.
Yeah. We put verification.
Again.
Yeah, again. We put verification into a lot. And the trade-off that you pay, that we're paying here, is time, obviously, optimization, speed. But here's the thought process is, how many times should we be changing the hours? Not that
You should only be changing them as necessary.
Yeah, not that much, right? If we're changing them, the extra couple seconds or the extra milliseconds that it's going to take to verify that the user actually knows what they're doing is gonna be worth protecting against a mistake, right? So when we do this in terms of, or for example, let's say, we take this and we have a different thing and we say, def, because you guys missed one thing, which is self.grades here. I know you guys don't want to even think about that, but add grade, right? How many times is this going to be being called?
Probably after every test or just every assignment. I mean,
A lot, right? And it's going to be called for every single student. So does the payoff for like adding an extra check for the extra time, if say we have 1 million students, does that make sense?
No.
It doesn't. So this kind of thought process is where you should be going with creating these data structures. Is kind of thinking about, well, how are they going to be used? So now that we've kind of like gone through that, how many of you know what a tree is?
Another data structure.
It is.
Mhm.
How do we create it?
Need a parent, and then I guess it depends on the kind of tree, but if it's strictly like, say, binary tree has a parent and like 2 childs or something like that.
Take it smaller.
A fancier linked list.
Yes, it is.
Pretty much.
What are the pieces of a tree? We're going to create a tree. I love this as a like data structure example because it's absolutely perfect.
branches.
Okay, so yes. How do we, but, so yes, there is a way to create a tree. We're not going to do it that way. We're going to do it in the leaf form. So a tree.
The class didn't go over trees yet, but some of us are already familiar with them.
Okay, we're gonna do an ASCII table. ASCII art.
Yeah, so Sophia, we've talked about stacks, briefly talked about queues, and then talked about lists and hashes or dictionaries. But yeah, we haven't gotten into, I guess, the more esoteric data structures like linked lists or trees or graphs, or we talked about sets. So definitely a lot of data structures to go over.
Okay, we're gonna go over trees briefly right now.
Good old ASCII art.
Love ASCII art, gotta say. I don't know.
Seriously underrated.
I know, right? I don't know if anybody noticed I'm a little old school. Okay, so trees, brief data structures lesson in objects. And then we're also going to go over this is a linked list. It's literally just an object that actually
So, question about the linked list, because I haven't used it in Python, but for like assembly language, is it just like the same idea as like assembly language in general, that each instruction has a next instruction?
I'm not going to answer that because I will go off on a tangent.
Okay.
So yes, it is. Assembly language doesn't necessarily work in terms, like doesn't work the same way in terms, sorry. We're going to stick to this.
There's that tangent.
Reach out to me if you want a lesson on assembly language. We're not going to go into assembly language because that is way beyond whatever you need to learn. So this
assembly.
Assembly. So this is a linked list. Literally, this is a linked list. You have a name, a value. You don't even really need this. You just point to the next node. And so what it really is imagine if you have like a, daisy chain. I loved to make those when I was a kid. You're literally linking the next daisy onto the chain. And you have to go through, you have to put the first one on before you can put the second one on, before you can put the third one on, before you can put the fourth one on. It's what I was describing in terms of a disk, a hard disk, where it's spinning and you have to go through the memory to be able to reach the piece that you want. So let's say you want D. You have to go to A, which leads to B, which leads to C, which leads to D, and you finally reached it. It's literally a chain, a linked chain. Questions?
So what would be the purpose of using a linked chain over other data structures?
I am so glad you asked. So there are really like two ways to do lists of things. There's an array and there's a linked list. Python, interestingly, always uses a linked list, even when you tell it to use an array. So linked lists, the cool thing about linked lists, you can always keep adding more. It's a never ending kind of like chain of things. The reason is because when we use a linked list, it uses what we just talked about earlier, which is a pointer. So it uses that pointer to the next memory location. When you use an array, it actually allocates a specific amount of memory, and they are all co-located next to each other. So the size, because it has that specific set of memory and that specific amount of memory, and then when you create something new, it creates something at the next memory address. You can't actually add on to an array. It doesn't get bigger. You can't get bigger and smaller with an array. This is dynamic and expands and contracts as you need it. So there are use cases for both of them. Let's say you know exactly how many records you need to store. Let's say you have a record store and you know you can only have 500 records at a time. You know how much memory space you need. But let's say you're expanding and you say, okay, I want to expand to a second location in the future and a third location in the future. You might want to be able to have that expansion, that kind of dynamic expansion, because you're going to be adding more records to your inventory as you grow. And so there isn't really a finite limit to how much you're going to have. So but at the same time, lookup is much more expensive because you have to go through everything that came before it. But it might not matter to you. You have to think about the use case of what you're doing. Did that answer your question?
Yes, I think so.
Okay, cool. I would really, if you're interested, I would really recommend so one of the things that I like to recommend people who are getting started in this kind of thing do is physically make these data structures. Like physically take boxes and line them up and go through things the way that the computer would, because and count your steps. So, it's kind of like counting the number of clicks that it takes to do a certain thing when you're doing front end. Take a few boxes or a few sheets of paper and stack them, stack them on top of each other and see how many pieces of paper you have to go through to reach the piece of paper that you want. Or perfect example, magic cards. I have a deck right here. I want to find this card. How many cards do I have to draw to be able to get there? I don't know if you guys can actually see me.
Well, usually there's 60 cards in a deck, so it depends how you shuffle. Also, it depends where the card's located.
Well, let's just say in terms of this, I know the order of these specifically. This is a commander deck, so it's 100. But I have a lot of cards here and I can't draw them out of order. So if I'm playing, I have to go through all of these cards in order to be able to get to this one. That's with linked list. If I laid these out on the table and you can't see it, but if I just kind of laid these out on the table and I could just see exactly where it was and I just pick it, then that's an array. The problem with that is I only have a certain size table. I can't make my table bigger when I get more cards. That doesn't work. I have to start stacking them. So that's kind of the benefit and trade-offs of the two. This is more compressed, but laying them out is faster.
That makes so much more sense.
Yay.
Sort of a time-space trade-off.
Everything is a time-space trade-off. Every single problem you solve, there will always be a better way to do it for different priorities. So when I think about building something, when I think about creating something, I think about what are the priorities. I usually go to whoever is, currently I'm building a new API, a new service, search service, and I'm going to the people who I'm building it for, and I'm saying, what are your priorities? And they go, okay, I want storage, like small storage, I want compression, high compression, and I want speed. And I'm like, well, then you lose redundancy. There's always trade-offs in coding. You can never get everything. There is no such thing as a perfect program. So always think about what those trade-offs are and what those priorities you have for what you're building are. It's impossible to create a perfect program. There's always a better way to do it for some different set of priorities. So this is a linked list. An array is that's a size 3 array. I can access any of them instantly, but I can only have that many. So now we get into kind of like where we kind of like came from. Okay, first of all, any other questions?
So which one's better for like adding to the end of the list?
This one. If you want to be constantly expanding or constantly changing it, this is what's better. A lot of the time, I'll use some combination of it. So I'll use some combination of, and I don't have the phones. I am just, sorry. So a lot of the time I'll use some combination, and once you get into like really kind of playing around with these and modifying them and building them and changing them, you'll get a feel for how they can be combined. So for example, like I can create a linked list, but I can create like an array of my own definition of pointers to a certain offset. I can modify them. You can create maps, you can create there are different ways to kind of like play around with them. But inherently you always have trade-offs. This is the better one for a continuously changing one. This is the better one for a set amount of a set, lookup, I guess.
So quick question, because you said in Python lists are structurally linked lists. So
not only are lists, actually arrays are structurally linked lists in Python. Python doesn't actually have in like behind the scenes, everything gets matched to a linked list in Python.
Got it. So as far as using these different things, all that is going to be different is the structure of how would that on the back end, how would that work as far as that aspect of Python?
So it's complicated. So they've done optimizations to make a linked list function more like an array, in terms of like what I was saying. The trade-off that they've made is space. So from my understanding, and it might have changed in kind of like Python 3.7 or 3.8, but from my understanding, they've taken a linked list and kind of like mapped certain pieces of it, and they have offsets. And so they've kind of like compressed the linked list. It's complicated. They've done some fancy data structure stuff for optimizations, but it is functionally a linked list in the back end.
I have a question to add on to that. Hopefully it doesn't get off on another tangent, but for the linked list, are we, by default, is it just a singly linked list or a doubly?
This one's a singly linked list. I don't know what's in Python's backend. I would assume it's a doubly linked list, but I don't know off the top of my head.
Okay.
The way that we're gonna go off on a small tangent real quick. The way that I would build a optimized linked list is by building an internal node class. I'm saying let's say next, and doing a self.next. I'm gonna ask you guys how this works after, but do self.next. So what I'm doing here is I'm adding offsets. I am adding a list, a smaller list. And what I'm going to do is I'm going to take and I'm going to add, say, every 5th node or every 10th node. And I'm going to add a pointer to that node. And what that does is when I actually go to look at something at the end, I can say, okay, I go through, it reduces the amount of computation time I need by 10 plus the offset of whatever I'm then going through. That may not make sense. But there's, so. Okay.
So like, say you wanted something like list was 10 spaces long, the offset was set to like 3 and you wanted 8. Could you travel along the offset until you get close enough and then go back? Okay.
Exactly. That's how I optimize a continuously expanding shrinking list. It uses more space, but it's faster for lookup. And so you reduce the time by a factor, which when you get to large enough inputs is significant. And again, like this is like I build indexes for a living, like this is kind of a cheat, and I work with like data that's like millions and millions of documents. So like when I reduce that by say like 200, like divided by 200, it's significant change. So this is just one way to optimize. Obviously I don't work with linked lists, but so now that we've finished that tangent on linked lists and stuff like that, Does anybody have any questions on how linked lists work? Or anything that we want to know?
I don't have any questions on linked lists. I have a question on, have you written down any of the Sophia theory in your head that's not proprietary that we can actually read and go through ourselves?
I do. I have not written down the Sophia theory, but some of my work is open source. So you can take a look at it if you want. My GitHub is Sophia Buell. So if you want to take a look. And yeah, I do some interview prep and stuff like that. Yeah. Okay, so we've been over linked lists. We've been over kind of like their connection to arrays. We're not going to go over stacks and queues. Well, we could, but we're not. How would you create a tree? That's this thing right here.
I'm sorry, can you say that one more time?
What is the, so you saw how I created a node right here, right? You saw how I created an internal piece.
So wouldn't you just create kind of in a similar way, create the head, and then each link of it will be linked to two, kind of for the tree structure that you have above?
Yep. Oh, I guess. Left, right. What's the problem? What are the issues that we'll run into with this definition of a tree?
If you wanted to have more than just left, right, if you want to have like more sub nodes to a given branch.
If we want to have more subnodes, yes. What else?
Do you not know when, I guess when you hit the end of the tree, you don't know when to stop?
Stop. What else?
Did we talk about the, I guess, the ordering, so to speak?
Expand on that.
This might get a little bit esoteric, but like kind of like the breadth first search versus the depth first search, where it's like, I know it's like one just reads like goes down and I don't know.
Back up.
Yeah, or something like that.
Yeah. Don't know where you are in the tree. Anything else?
Don't know if this is just a functionality of the tree, but if you're on one side of the tree, the other side is inaccessible.
Yep. So you can't go back. So that's kind of like what he was saying. You can't go back up. Anything else?
Do you know exactly what you're actually looking for in the tree? So I guess having almost like a variable to check against as you're going through each item.
What else? There's something else.
Does it know what where to start at?
That's kind of like you don't know where you are. There's something else that's a feature of a linked list as well. I think you unmuted yourself when you're talking.
Oh, sorry. I was gonna say the head versus the tail of the linked list. Or would that be kind of something else on there.
That's, yeah, that kind of fits into the don't know where you are.
Okay, never mind.
You have to go through every node ahead of another one in order to get to the one that you're looking for. You have to go through the entire tree possibly to get to the node that you're looking for. Right. So we're going to start with, I'm just going to check. How long do I have for this class again?
Not as long as we have a schedule till 1, but as long as you want. But
because I'm on like California time, so I was like, I don't know when the okay, so you have to traverse the entire tree to search, right? So these are all problems with this like basic things. What are the benefits to this?
It's divided up, so even though you have to travel through each head to each node, it's less that you have to travel through compared to a linked list.
True, I wasn't comparing it to a linked list. So what are the benefits of this definition of a tree compared to other definitions of a tree? Like what are you looking at here? For example, like small amount of code, easy to read.
I was gonna say better organized, but that kind of ties into that.
Well, you hit the right on the head. But there's another piece of it that's really good. It takes up no space. Right?
Are you referring to like memory space?
Mm-hmm. There's a left and a right, and that's it. And they can be null. So this is what I mean when there's always trade-offs. The minute you solve one of these problems, you give up something here. So let's solve one of these problems and see what we give up, right? Let's take with more subnodes. How would you solve that? How would you solve that piece of it?
You can just add more parameters, left, right,
Do
center.
it like a getter setter of tree. When you need more than left, right, you have the means to add a branch or a child.
That is definitely one way to solve it. That's actually my favorite way to solve it, but I'm picky sometimes. So you just can do an init. Self dot equals empty list. No semicolon. Okay. This solves the multi-node. What does this take away? It's the
More space, not as easy to follow.
Takes longer because you don't have the sub nodes to kind of skip around.
takes longer to find tag. What else? There's something else that's really important like aspect of this.
because I guess because there's more code, there's more likely for you to create or introduce bugs, I guess. That might not be what you're asking.
I mean, that's a very, very valid point and very good observation.
It does introduce another data structure within it. Like you're calling a list within.
It also removes the location aspect of the children. You don't have a left and right anymore. I mean, you can infer from where they're located, but what if you add the right before the left or the left before the right? It's just a child now. There's no location, there's no kind of like location side piece of it. So this may not be a problem for someone. This may be a problem for someone else. You have trade-offs. Solve another one. What about can't go back up? How would you like to solve that?
Some kind of like tiering identifier that's associated with each like tier down into the tree if you go, or is that totally the wrong direction?
No, I mean there's no.
There's lots of ways, of course.
There's a ton of ways, and I'm not married to a single way to do things. That's one of the pieces of like, you know, you come in and you have to, especially in code, you have to be able to work with people and you have to have an open mind to be able to kind of like adjust to how people would like want to do it, or, you know, what their suggestions are. So I had a different way in mind, but your way is totally valid, and it is an absolute, like it's also a normal way to do it. So we're going to do it your way.
I'd prefer you did it yours.
Well, the way, I mean, we can do it both. So I don't know, there's a R word that is usually typically used for that. But I cannot, it's on the tip of my tongue and I can't remember it. So level, do we want to do a multi-node or a set amount of children?
I guess we go with multi-node.
Okay. Okay. Oops. What about this one? What does this one do?
Would you, just looking at the functionality of it, would it be traversable? Like you could go up to a previous level, but wouldn't that erase the data that's on that level? Like, wouldn't you need like a nested list or something to save the children to that level specifically? Or
I like the way you're thinking. So this actually doesn't solve the traversal problem. It does solve the fact of you know where you are in the tree and you know that you're like not the top, but it doesn't solve the traversal problem. You still have to start over every time you want to go. So I'm going to write another one. I'm just kind of going through and showing you the different ways that we can build on these things and the different considerations that we take into account. So an actually traversable tree would have a pointer to its parent. See the difference?
So I have a question.
Yeah.
On line 80 and line 78, besides the parent, I don't really see the difference in syntax.
So, and this is where typed things come into play. What is the level?
It's the level. Okay, so let me just rephrase what I'm commenting on. Because you named it parent, then you have what you have, but because you named it level, they're basically the same thing, just name something different.
So this is where Python gets hard to teach data structures, because we're going by what we expect those variables to be. In this case, we expect, in this case, we expect it to be a number value. So we expect this to be the numerical kind of level of where it is in the tree. It doesn't actually give you any ability to retrace your steps.
Oh, okay, that makes sense. Got it. Now that you said what you said. Okay.
Yeah, this
Well, in that sense, would it just be like a marker then?
give me one sec, because I'm going to finish this for some people who might not have followed the entire way. This one gives you what we were talking about before, a pointer to the previous place where you were at, to the next level up. And from that, you can traverse backwards. You can retrace your steps through the tree. So if you're searching for something, this is incredibly important, because you don't have to go through the entire tree again. Okay, what's up? Sorry. I can't see names, so I'm just gonna go with white sweatshirt dude.
I guess that's me. So how would you go about traversing the tree then if you just set, I'm assuming the self.parent would just be a marker for to kind of like point above children?
The self.parent is actually a traversable tree. It's actually so the way that it would work is that these now point both ways, these right here. So this B points to A and A points to B. In the same way that we point to children, we now point up as well to parent. Does that answer?
So you're invoking it to basically allow it from instead of just pointing from A to B, you're initiating it to be able to traverse back up.
Exactly.
What would be the technical term be called for that, where two different values point back to each other?
And that's where we went to, it's a doubly linked list.
Okay.
Or it's doubly linked.
Okay.
So it's both directions. Took me a second to like get the mirror image down to like do that with my hands. So we've solved kind of the traversal problem, right? So that was can't go back up. What did we introduce? Like what?
Time.
Oh, sorry, go.
I was gonna say induce more time because now it's looking in more areas for the particular data.
More time in terms of like more time to traverse or more time to
A runtime in particular.
actually no, we sped up the runtime.
Gotcha.
You end up using more space, I guess, because it costs space to have to put the location on both values.
Yes. But we haven't used that much because what it is it's a memory address, which is a numerical version, which is 128 bits. So it's not that big, but it is a size, you know, it is something. So we always like, it's important to keep in, you know, the trade-offs, like I was saying. We've definitely introduced more space. It's not that much, but it is something. And those somethings, those little somethings add up pretty fast when you're doing something, you know, like this. So that's pretty much, oh, yes?
Would you still say that in this case we've lost the location aspect because it is like a multi-child setup, or because as pointers we haven't?
I would say we have lost, we still haven't solved the kind of like, we don't know where the children are, you know, in relation to each other. We don't have a set definition of that. Yeah.
Just question as far as like functionality of this, because I'm getting a little, just for my clarification. So in instantiating this, you would instantiate the parent node, and then you would instantiate a child node, and that's what would link the parent to the child kind of thing. Like so the one instantiation would have the parent and the children, and then the next instantiation would be one of the children which have those children to it. Is that how that would work, or is that how?
I think I understood you, and yes, I think that's how that would work. So I guess a better definition of this would be you have subtrees and it's pointing to its parent. It's a self-contained thing. The tree above it is pointing to it as a child. What could we do here? Or what were we able to do in all of the other ones that we aren't able to do here?
Can you elaborate on that?
I know there's
something, there's a feature that we were able to do, and some call it a bug, but I call it a feature, that we were able to do up here in every other version that we've now locked here. We've defined something new and it's locked in a quality of the tree that we didn't previously enforce.
Isn't there the possibility of like there's not a single path, so because it could go backwards, it could ideally go back and forth and lead to like infinite movement or anything like that?
We're onto something. So we have introduced potential cycles, which is where you go in a circle, because computers don't understand gravity for trees in a sense. But you're onto something with kind of like being able to change that.
You've hard coded the parent, so as of right now, you have no way to change it.
So we have hard coded. More than that, there's something else about the parent that we've enforced.
You've made, I guess, the value is pointing to always the child. And so I guess, does the child become a parent on the next iteration, or does it stay as a child?
We always say the parent, right?
Mm-hmm.
What about a parent?
So you're saying you can't have multiple parents in this kind of tree?
Yes. We've enforced that. One of the really important things to do when you're creating data structures, when you're building these, is to not be locked into your previous understanding of how this data structure works, not make assumptions. If you're making an assumption, it needs to be hard coded. Back here, we were all making an assumption that there was a single parent, but that wasn't necessarily true. I see you talking, Stephen, and I think.
Oh, I was talking to myself. I was wondering, like, how are these like parents and child nodes like ordered?
That's the thing. They're only ordered by their connections to each other.
Okay.
So again, you need to always take the image that you have and go through and say, what are the assumptions that I'm making? And the assumption is that they're ordered. The assumption is that they're, that a child doesn't point to its parent as a child. The assumption is that the child doesn't point to a root as its child. The assumption is that they're in a straight line. We haven't enforced that, right? So that's not necessarily true. They can be cyclical. They can be, multi-parent, multi-node children. They can be, pointing to each other. They can be pointing to themselves. It's important to look at what you're building and say, what assumptions am I making? How can I break this? What can I do to create something that I don't expect? And that gets into testing. Yay. But before we kind of go into that, what are the questions?
I guess just in looking at this, because I would think that the tree that I would want to make would be each node is assigned a list. The first object on the list would be level, second object would be the parents, third object would be the children. But that, I guess, would just take up a ton of space and be less time oriented.
So I'm going to tell you that that's the abstraction. Remember how we went through how it's actually functioning in memory?
Mm-hmm.
That's how the memory writes it.
Okay.
So physically, on the memory, it's a block of memory, and it's a list of, this offset, like this spot in the list starts the size. This spot in the list starts the child number 1. This spot in the list starts the child number 2. It's literally, I wish I had a whiteboard. It's literally a array as you think about it. But the coding language abstracts that for you. Okay. The compiler abstracts that for you, which is, nice.
I guess the follow-up question to just this line of thinking, if you have nodes that are, so you can't have nodes that are the same name, or because it seems like the only thing pointing to a node is its name. So you can't have nodes that are the same name, or else I feel like wouldn't know what to point to, right? Off that.
Can you repeat that a little bit?
So like say a node, a parent points to a child and the tree goes down more, but then if somewhere else down the tree you have a child named the same thing, then I feel like it would break the tree because it wouldn't know what to point to. Or are each of these individual nodes looked at as a memory location, like an individual specific
Yeah.
one? Okay.
Yes. Yes.
Okay.
So name is a human construct. The computer's definition of a really important thing to do is switch from thinking about names to thinking about unique IDs or memory addresses. That's the computer's identifier for, it's like a social security number. It's a unique identifier for the location and memory of that piece. They can have the same name, they can have the same values. They're still different physical objects if you create it twice.
Hey, Sophia, are we able to take a quick 5-minute break?
Yes, I was actually about to say that because I know that like sometimes my brain just like races ahead and people get tired. So yeah. Yes.
All right. Yeah, so let's take a quick 5-minute break. Be back at 11:33 or 32, and we'll keep going.
And I'll be right here. So yeah. Have some coffee.
Absolutely.
You said you were going to NYU, but you said you were in Northern California. Are you so you're going to NYU